Hello everyone, I'm happy to see you again on my channel. Last time we talked about the one-dimensional univariate empirical mode decomposition, and in this video we go one step ahead and take a look at the multivariate empirical mode decomposition, in short MEMD. But what does multivariate mean in this context? Well, instead of only decomposing a single one-dimensional signal as we did with the univariate EMD, we now simultaneously process multiple one-dimensional signals. These signals can be different quantities that we measured simultaneously, for example velocity components, temperature and pressure data from a single experiment, or they can reflect the same quantity that we have measured several times to study the repeatability of the specific experiment. As you know, we perform a decomposition to separate our data into several components, which allows us to analyze the data from a new perspective and obtain novel insight into data inherent features that are not observable using the complete data. Using the EMD, these new components are called intrinsic mode functions, in short IMFs. In the multivariate framework, we are specifically interested in analyzing how different signals are related. So we want to extract on which timescales, or rather frequencies, and at which time intervals our signals behave similarly. Let's see why the multivariate EMD is a very powerful tool for this. Here you exemplarily see three time-dependent signals. Using the univariate EMD, we would decompose each signal separately, and since we are interested in the signal's relation, we would subsequently compare the different IMFs across the three signals and search for similarities. However, our signals usually possess different characteristics, and using the univariate EMD mostly results in a mode misalignment. This means that, for example, the second IMF of the blue signal does not comprise the same range of scales as the second IMF of the orange or of the green signal. And it is also likely that we do not obtain the same number of IMFs for each signal. So it is not clear which IMFs we should compare if one signal produces in total 6 IMFs and the other signal 7 IMFs. To tackle these issues, we need a multivariate EMD. And this method simultaneously decomposes all three signals, but we still obtain one individual set of IMFs for each variate. Now, by constraint, the second IMF of the blue signal contains the same range of scales as the second IMF of the other signals, and the same holds for the other IMFs. Consequently, we can directly see if the signals have comparable timescales by comparing equal indexed IMFs. We call this the mode alignment property. You might have heard of other multi-component EMDs like the bivariate or the trivariate EMD. For generality, I prefer to directly study the concepts of the multivariate algorithm, and you can still use this one if you only have 2 or 3 signals. Okay, now that you have an impression of why you should prefer the multivariate EMD over the univariate EMD, if you want to analyze more than a single signal, let's start with digging deeper into the method. Rehman and Mandik were the first who introduced the multivariate EMD to the community in 2010. They also provide the MATLAB code online, so if you want to try the MEMD on your own data, you can start right away. I have also used their implementation on the data we will now discuss, which are the 3 signals plotted on the left. I call them G1, G2 and G3. They are time dependent, but they could also depend on a spatial coordinate. I have constructed these signals by superimposing different combinations of sine waves. In total, I used 3 sine waves with different frequencies and added 2 or 3 of them together with different amplitudes. You can also see that I have added a constant offset from 0 to the blue and the green data. But I guess you cannot see at a first glance which signals contain the same frequencies. So we have now constructed a synthetic test case in which we want to analyze which frequencies are common to the blue and the orange signal, the blue and the green signal, and the orange and the green signal. And the good thing is, I know the right answer, so we can check the validity of the method. We start by concatenating the three signals to form a matrix G that builds the input to the MEMD. After doing its magic, which we will soon discuss, we obtain the following IMFs. In the top left, you still see the original signals and the corresponding modes possess the same coloring. We can see that the sine wave with the highest frequency, f1 of 300 Hz, is contained in each signal, since the first IMF of all signals looks similar. Let me zoom in on this first part here to clearly show you the similarity. Here you also see that the amplitude changes among the different variates. And this is because I've multiplied the sine wave with 4 for the blue signal, with 5 for the orange, and with 3 for the green signal. So the MEMD is not only capable of showing us common timescales or frequencies, but it also shows us the corresponding strength expressed by the amplitude. Let's check the next IMF. We see that this specific frequency of 120 Hz is not contained in the orange data. Its IMF is nearly 0. Since the sifting process is never perfect, we will always have minor deviations from the true data. But we clearly see that this mode has no significance for the orange data. The overshoots you see near the boundaries result from the spline fitting, since the number of extrema reduces near the edges and there's just not enough information for precise fitting. There are enhanced methods to tackle this issue, but we are not covering this today. The third IMF shows a frequency of 50 Hz that is contained in the orange and the green, but not in the blue data. As for the other IMFs, you can also extract which amplitude are used for each sine wave. An amplitude of 5 for the orange and a factor of 3 for the green signal. The remaining residual contains the offset from 0 if it exists. So for the blue data, I used a constant of 5, and for the orange signal, the offset is 3. So in summary, you can clearly identify which frequencies, amplitudes, and constant offsets I have used to construct the three signals. This shows us how well the MEMD aligns scales that are common to 2 or more components of the multivariate input data, and it presents these relations in an easily understandable way. I wrote down the complete signals here, so if you want to compare the terms with the resulting IMFs at your own pace, please feel free to pause the video and make sure that you can relate the different components. Let's quickly summarize. We have seen that the MEMD provides a set of IMFs and a residual for each variate. As for the univariate EMD, the mode adherence scales increase with mode number, so the frequencies decrease. And the multivariate EMD is also complete, which means that the sum of all IMFs and the residual gives us back the original data. Okay, we have seen how the MEMD performs on a multivariate dataset and which useful information we can extract with it. Now, I guess you're curious to figure out how the MEMD actually works. For this, we will briefly take a look at the univariate approach and check which steps we have to modify for the multivariate version. If the EMD is a brand new topic for you, I highly recommend to watch my previous video in which I explain the working principle of the univariate EMD in detail and then come back to this point. You might remember this figure from the previous video. Our original signal f of t is the blue curve, and we determined its extrema in the first step. Then we fitted an upper and a lower envelope through the maxima and minima, which are shown in orange and red in the figure. We determined the mean of these envelopes, which is the green curve, and we subtracted it from the original signal, which then gives us the violet signal, the residual. Don't be confused by the notation that is used in this formula. In the first iteration, res subscript I is the signal f of t, but it is replaced by the outcome of this sifting in the second iteration of the inner loop. We will take a detailed look at this in a moment. So for the novel residual, we check a stopping criterion, which basically compares the deviation of this residual from the previous residual, or in the first iteration, its deviation from the original signal. If the stopping criterion is not satisfied, we have to repeat the sifting using the residual instead of the signal f of t. And this is the inner loop, and it is repeated until the stopping criterion is fulfilled. If the stopping criterion is satisfied, the residual is our first IMF, and we would repeat the sifting process with the updated signal f of t that remains after subtracting the new IMF from f. This outer green loop gives us the next IMF, and we perform the sifting until our residual is a monotonic function from which we cannot extract any extrema. Okay, now that we have refreshed our memory about the sifting process, for the univariate EMD, we can think of possible differences for a multivariate instead of a single variate input. It is actually the very first step that is not easily applicable to multivariate data. Finding local extrema in multivariate data is not straightforward, since higher dimensional fields like complex numbers and quaternions are not ordered. So you cannot state if one complex number is smaller or greater than another complex number. This obviously inhibits the determination of local extrema. To circumvent this problem, the key idea is to use projections of the multivariate data in the real number space that allow the determination of extrema. So before we can even start with the sifting process, we must select suitable projection directions for our data. We project our data along these directions, and then we can determine the local extrema of these real valued projections. Now, this is important. We do not take the values of these extrema to determine our enclosing envelopes. Instead, we take the values of the original multivariate data at these extrema locations. So the projections only serve the purpose of telling us at which time instances the local extrema occur, because we cannot extract this information from the multivariate data. But to precisely determine the enclosing envelopes, we use the multivariate data again. Once we obtained the envelopes, we can proceed similarly to the univariate EMD. We determine the mean envelope, we subtract it from the input data to obtain a residual, and we check if the residual fulfills the stopping criterion. The only difference is that the involved quantities are not univariate signals, so they are not vectors, but they are matrices whose size depends on the number of variates. And the stopping criterion differs to tackle the changed data properties. Okay, after this high-level overview, we will take a closer look at the individual steps, especially the projections, to really understand how this process is working. For this, we will use a trivariate signal, which means that we have 3 individual variates or signals. This is convenient since we must use multi-dimensional space for our projections, And the number of spatial dimensions equals the number of variates we want to decompose simultaneously. So trivariate consequently means three-dimensional, and we can easily visualize the procedure in 3D space. However, using the data g of t that we previously looked at is not an option, since it makes a really nasty 3D plot and it will be quite difficult to explain the procedure using this data. So we will use a more suited trivariate signal that has a nice shape in 3D, as you can see here on the left. The two other figures just show the top and the front view. Note that the sines and cosines of all three signal components have the same frequency f1, so the resulting modes won't provide us with novel findings. We just use the signal for visualization purposes. Okay, for our decomposition, the main objective is the determination of a local mean envelope, so that we can calculate an IMF, or at least a residual that brings us closer to the actual IMF. For a signal with only one dimension, this is achieved by defining an upper and a lower envelope via the signal's extrema, and this upper and lower envelope enclose the complete signal. Then we take the mean of it. In 3D, we can imagine a tube-like object that encloses the complete data, which looks like an ellipsoid for the present data. This enclosing structure is a 3D envelope, but it is quite challenging to define it, especially when it comes to higher dimensional space for multivariate signals with more than 3 variates. So instead of calculating the complete envelope, we approximate it by discrete curves, which could look like these black lines here. We denote the total number of individual envelopes by capital K. If we calculate enough of these individual envelopes, their mean envelope approaches the true mean envelope of the three-dimensional enclosing structure. Therefore, it is important to have a uniform distribution of the individual envelopes. If they are not uniformly distributed, their mean might not reflect the actual mean envelope we want to approximate. And this is where the projections come into play. We use uniformly distributed direction vectors that guide us to evenly distributed enclosing envelopes. And to make our life a bit easier, we can represent these direction vectors as points on a unit sphere. So our objective shifts to finding a uniform sampling scheme on a hypersphere. The sphere's dimensionality is defined by the number of variates capital N. So for our trivariate signal, which lives in 3D space, capital N equals 3, and we use an n-1 sphere, so a 2-sphere. Don't be confused by this notation. Since we only consider the surface of this 3D ball, we do not need the three-dimensional volume it contains. And its surface is basically a plane that lives in 3D space. That's why we call it a 2-sphere. You see a uniformly distributed point set on this sphere in this figure here, using 64 points. It is obtained by a low discrepancy Hammersley sequence, which proved beneficial to obtain uniformly distributed point sets. Once we have this point set, we can easily define the corresponding direction vectors. Here you exemplarily see 4 of such direction vectors. Just imagine the direction vectors as vectors that point from the origin to each point on the sphere. And we can find points either by the coordinates associated with each direction vector x or by the angle theta. Both uniquely define the points on the unit sphere. So for the present data with 3 variates, each direction vector has 3 entries, 1 for each coordinate direction. And as we increase the total number of direction vectors, we also increase the accuracy of our resulting mean envelope. Okay, so now you hopefully understand the key aspects of the MEMD algorithm and why it outperforms the univariate EMD when you want to compare features of multivariate data. In the next video, we will walk through each step of the sifting process in detail using our signal g of t and the 4 exemplary projection directions to see how everything is lined up. Thank you very much for watching, and I will see you in the next video. Bye!